Yesterday I introduced you to the concept of the velocity field, and then the concept of streamlines, and I think we finished with an example of how to calculate streamlines, if I'm not mistaken. So the next concept that I need to introduce to you, which is related to the velocity field, is that of pathlines. Let me remind you that streamlines are essentially the field lines of the velocity field, v of x and t, at fixed t. So you fix the value of the time, you substitute value for t, 0 seconds, 1 second, 2 seconds, 10 to the 58 seconds, whatever value you wish to substitute. You then are left with a function of x, y, and z alone, and you solve the equations dx I by d lambda. Lambda is some parameter, and these are equal, so this is a set of 3 equations. I can take values 1, 2, and 3, and so you duplicate or replicate this equation 3 times, 1 for each value of I. And this is a function of x, y, z, and the fixed value of t. But the value of t is fixed, you've substituted a number for it, so the right-hand side is a function of x, y, and z. And this gives you a set of curves in a snapshot at fixed time of the fluid. The curves tell you something about the structure of the velocity field. It doesn't tell you how the fluid moves. It tells you the structure of the velocity field at this fixed time. The structure will change with time because if you substitute different values of t into the last argument, then you will be solving a different set of equations, and so you expect the solutions in general to look different. So this is important, fixed t for streamlines, and the streamline pattern, the set of curves that describe the streamlines, give you information about what the velocity field looks like at that fixed time. It does not tell you how the fluid actually moves. So the next thing we have to consider is, how does the fluid move? If it's not according to the pattern produced by the streamlines, then how does the fluid move? And for that, what we need to do is calculate what are called pathlines. So a pathline is the actual path followed by a fluid point as it moves. Another way of saying this is that a path line is the trajectory of a given fluid point. So this is the actual path that is traced out in space by any fluid point on which you focus your attention. And we need to set up the equations that give us this path, and for this we use the definition of the velocity. The definition of the velocity is that the ith component of the velocity is the rate of change with respect to time of the position coordinates of the point of interest. And so what this means is that to get a path line, we integrate the equations dxi by dt is equal to vi of x, y, z, and t. Now, staring at that equation, you may be saying to yourself, isn't that the equation that is sitting on this board over here? So that is my question to you. Isn't that the equation that is sitting on the board on this left-hand side? No. Why not? Oh, yes. So there's a t here. Here is one difference. Yes. Any other differences? Ah, yes. If you can't see the difference optically, because I didn't make a difference, I should have written T0 maybe, or T tau, or used a different symbol to show that the time is fixed. But this argument is fixed. And here, T is one of the variables. So they are actually different equations that we're solving. We're not fixing the time when we work out the path lines, and we are working out the rate of change of coordinate to a point with respect to time. We're not setting up a parametrized form of a curve at fixed time. So these, in spite of superficial appearances, these are in fact very different curves. Right, so this set of curves, that is the ones that describe the streamlines, tell us what the pattern of the velocity field looks like at any given instant. The path lines, on the other hand, you will get a set of curves here as well, in general different from the curves that you get on that side. And these curves, which wend their way through space, tell you the actual path that is followed by the fluid points as the fluid moves. Alright, I've set up some tutorials, so I will give you examples to work out before Wednesday. I will send them out later this morning, and that will illustrate to you the difference. First of all, it will illustrate how to calculate using this equation, the path lines, and it will also illustrate the difference between path lines and streamlines, because I will be giving you examples where the two are radically different, and I will be asking you to compare the patterns that you get from us. For the moment, simply note that they are in fact different equations, in spite of superficial appearances, and therefore you expect in general different types of solution. The next question is, given that these equations are different and they produce different sets of curves, are there any circumstances under which you might expect the solutions of these two equations to be exactly the same? In other words, is there any situation in fluid flow where streamlines and path lines might coincide? Yes?
Just because it's 8 o'clock. But a constant velocity not be useful?
Constant velocity?
Like the velocity that's not changing direction.
Yes, a constant velocity would do that. But why? And furthermore, the answer is too special. You've produced an example, you haven't given me a condition on which the two would coincide. Any ideas? Well, to get the same set of curves, you must be solving the same set of equations, must you not? Does that occur at any time? All right, so suppose the velocity doesn't depend on time. Then there is nothing to fix in this equation. And if the velocity doesn't depend on time, then you have on the right-hand side exactly the same field for all time. And it's now just a matter of cosmetic indulgence as to what you call the path parameter. So the fact that you're calling the path around to lambda here and T over there. This is just a change of name. It's like people who get tired of being called Fred, and they go to the registry and they get their name changed to Charlie. And you must be a Charlie. You change your name from Fred to Charlie. So, if the velocity field does not depend on time, then these two equations are identical, two sets of equations are identical, and under those circumstances, pathlines and streamlines will coincide. So, in general, pathlines and streamlines do not coincide. When you see a picture of streamlines, do not make the mistake of thinking that these are the paths that are followed by the actual fluid particles in their motion. The coincidence occurs only in the special case. Where V does not depend on T. And this is called a steady flow. Or a stationary flow sometimes. Stationary does not mean static. Static means at rest and not moving relative to your coordinate system. Stationary means the conditions do not change with time. So, under these special circumstances, then pathlines and streamlines are one and the same set of curves, and we therefore have no difference between streamlines and pathlines. When you calculate one, you have calculated the other. Now, in the notes that I've sent out, I discuss how you might try to do a solution of these two sets of equations using computational methods, and in those notes I follow the computation to the third step rather, and show you that already at the second step, the numerical computation of pathlines and streamlines begin to diverge, which shows you that they have to be different. And the reason that they diverge is because of the time dependence of each of these two sets of equations. Work through that as an exercise, make sure that you understand exactly why it is that pathlines and streamlines in general are very different. All right, the last concept that I want to discuss is not one that I'm going to do in detail in the lectures. I need to mention it because there is a temptation, and we all give into temptation. There is a temptation to think that when you look out of the window and you see smoke rising out of a chimney, that you are watching either streamlines or pathlines. And the answer is you are not. These are called streetlines. So a street line is not the path followed by some overzealous rugby supporter who pulls his clothes off and runs across the field. A street line is a technical term in fluid dynamics, and a street line is the locus of points at given time t. Of tracer or marker particles, I'll explain that in a moment, released into the fluid flow feed. So if you look out of the window and you see smoke rising into the air, and it forms a pattern, you know, it rises slowly and then it gets pulled sideways by the wind. What is happening is that you are injecting something into the fluid that is easily visible to the eye. This, in fact, is how the engineers try to understand the nature of fluid flows. What they do is they take some syringe-like bit of apparatus, they insert this syringe into some position, fixed position in the fluid flow, and what they do is they then release a dye into the fluid, the liquid in this case, or smoke if it is a gas. And as the gas moves, of course, this stream of dye that you've released will form a particular shape. So you are releasing the dye from the same position. It's called a tracer or a marker for obvious reasons, because you want to be able to follow it visually with the eye, and you release it from a fixed position in space into the fluid as the fluid flows. And each one of the particles at every instant tau following the initial release, at every instant tau a particle is released. And what you're looking at when you take a photograph, that's what your eye does effectively. It forms an image, an instantaneous image in your mind of what is happening outside. The image changes with time, of course, but you form an image at a fixed time, and what you're looking at are the positions of all of these marker particles that have been released from the initial time right up to the time of observation. Right? And that is called a street line. In the notes, I give you a method for calculating the street lines. Street lines are much more difficult to understand in terms of calculation than either path lines or streamlines. But they are useful because this is often the only way that we have of visualizing flows that are set up in the laboratory or under terrestrial circumstances. All right, so this completes the section on the velocity field. Is there anything that you would like to ask on this particular section? Yes?
Is it necessary for this definition for the trace on marker particles to be different to particles otherwise it's path?
No. The street lines are different from the path lines.
Yeah.
You solve a different set of equations to get the street lines than the ones that you solve for either path lines or street lines. So the solutions are different. They're very different curves in space. Again, when the velocity field does not depend on time, the street lines will coincide with both path lines and streamlines. And so under those circumstances, if you have a steady flow, then you can actually see the path taken by the fluid particles by observing the street lines, but not in general. Initially, when people started to use these methods to try to visualize flow, they thought that streamlines and path lines would be the same. But in fact, when you work out from the definition that I've given here what the mathematics is, it turns out to be different sets of equations and something that coincide. To answer the question that you asked directly, the tracer particles in principle do not need to be optically or visually different. However, if they are not, then there's not much point in having tracer particles. Incidentally, this is how oceanographic studies are carried out. What they do is they release particular tracer materials into the currents that flow around the oceans, and they then have different stations where they detect the concentrations of what they've released into the various currents, and that's the way that they track what the currents are actually doing. Any other questions?
What if you're injecting the tracer particles into something that is intermediate, whose velocity field isn't very it doesn't have a big magnitude? How would you then differentiate between the velocity with which you inject the tracer particles and what the flow is doing in the injecting.
All right, so when you inject tracer particles into a flow, you try to do it in such a way that the tracer particles are as close to zero velocity relative to the fluid as possible. In fact, not relative to the fluid, relative to the point at which you are doing the injection. So for example, if you drop a small piece of potassium permanganate into water and then get the water to flow, that potassium permanganate, the particles are coming off at almost zero velocity, and they are then carried by the flow. They are in purple colour, so you can actually see visually what the flow is doing from what the particles are doing. Any other? Yes?
Would that change the pattern with which the fluid is moving? Because now there is an introduction of new particles, which means there are more particles compared to the fluid volume of the fluid. So would that change the way the particles the fluid move?
Yes, but the number of tracer particles that are injected is so small by comparison with the total number of particles in the fluid that it really doesn't make very much difference from that point of view. You're talking about orders of magnitude difference in the numbers of particles. Other questions? Right, well, let's move on then. The next topic in kinematics, having studied how to describe velocity, the velocity of the fluid points as they move, what we must now do is study how they accelerate. Why acceleration? Because eventually I want to apply Newton 2 to a set of fluid particles and work out from the forces that are acting on those on the fluid particles, work out how they will accelerate and subsequently how they move. So the next topic is fluid acceleration, and it is under this topic that you can see the dramatic difference that there is between the description of velocity when dealing with point particles, the motion of point particles, and when dealing with a continuum of particles. This is fluid acceleration. What we need to do is focus attention on a single fluid point. So consider a single fluid point. Then, the velocity, by definition, of this fluid point is the velocity at time t plus delta t minus the velocity at time t divided by delta t. And, well, this gives you the average velocity. This is the same definition as you have for point particles. And then as you allow delta t to become smaller and smaller, in other words, in the limit as delta t goes to 0, this defines my magnitude velocity over there. This is acceleration. I beg your pardon. You complained it was 8 o'clock in the morning, so I'm going to make the same complaint now. What's good for the goose is good for the gander, isn't it? So this is the acceleration. It is the velocity of a point at time t plus delta t minus the velocity at time t, and divided by delta t in the limit as delta t goes to 0. This is the rate of change of velocity. The difficulty that we have is that we don't actually know the velocity of the particle as a function of time. What we have is the velocity of the fluid as a function of position and time. And so what we need to do is interpret this definition in terms of the description that we are giving of the velocity. So at time t, suppose the particle point rather the fluid point is at position x. Where will it be at position t plus delta t? What this means, it is at position x at time t. What it means is that the velocity of the point is equal to v, the velocity field, evaluated at position x and t. So in time delta t, so here it is. Here is my position x. It's where the fluid point is that I'm considering, and it is at time t, and so it has a velocity v. And this is the velocity that is produced by substituting the values of the coordinates and the time into the velocity field that describes the motion of the fluid. So in time delta t, this fluid point displaces by an amount, well, to where does it move? It moves, so here is its trajectory. This is the path line of the fluid point, and it moves to a position, a new position on the trajectory, which is approximately, so this is x plus delta x, and it is, I'm looking at its position at time t plus delta t, and the amount by which it has moved, of course, this displacement delta x is going to be approximately the velocity that the particle will have times delta t. I say approximately because, of course, if the velocity field is not is changing with position as you displace, then the trajectory will not be a straight line. But we will get the right answer when we take the limit as delta t goes to 0 eventually, and so this approximation will become accurate. So, at time t plus delta t, the velocity of the fluid point, so that it's now, I'm now calculating the velocity that it has at this position, x plus delta x, and this velocity, how do I get it? I substitute the value of the position and the value of the time into the vector field, and that gives me the velocity that it has at position x plus delta x and time t plus delta t. And so at time t plus delta t, the velocity of the fluid point is v at x plus delta x, t plus delta t, and the problem now is to find the difference between the new velocity, which is given to me by v of x plus delta x, comma t plus delta t, minus the original velocity, which is v at x and t, divided by delta t, and that will give me the acceleration of the fluid. Right, so that's what we're going to do. Delta x, if delta t is small, delta x will be small, and so I can get an approximate form on the Clarence series. And we will eventually take the limit as delta t goes to 0, so these approximations will become accurate in that limit. For delta t small, delta x is small, because delta x is proportional to delta t, and what that means is that v at x plus delta x t plus delta t is going to be, well, I'm going to work out the McLaurin series. I'm going to work here with the, no, I'll leave it like it is. And so this now becomes v x and t. I assume that you know the Taylor series for multivariable functions. The next term will be dv by d argument. So this is dv, I will write it out in full first and then I will abbreviate it. dv by dx, and x and t, it's evaluated at the original values, x and t, multiplied by delta x plus delta v by delta y at x and t, delta y plus delta v by dz at x and t, delta z plus dv by dt at x and t, delta t. And then you get the second order terms plus 1/2, and then it is d2v by dx squared at x and t, delta x squared plus the remainder of them, and I don't propose to write them out because we don't need them. You'll notice that this is a summation which involves, that is the terms 2, 3, 4, and 5. They constitute a summation which involves x1 delta x1, d by dx2 delta x2, d by dx3 delta x3. And so I can use the Einstein's motion convention in order to express these. And my formula then becomes v x and t. Plus, I'm working in Cartesian coordinates. I suppose I don't need to emphasize that. I'll show you how to do it in different coordinate systems. This now becomes dxk, evaluated at x and t, times delta xk. And because I'm not a space-time physicist when I do classical fluid dynamics, I'm a classical physicist, I separate space and time. Were you a relativistic physicist, you would combine these four terms into a single term by calling T, or rather C times T, you would call that x naught. But I keep them separate because we're doing classical physics. Terms which I have invented, that's all terms of higher order. Oh, I've got a v of x and t that appears on the right-hand side. Isn't that interesting? Because in this definition that I worked out, I need the velocity of time t plus delta t, which is given to me by this quantity, v of x plus delta x, t plus delta t. I subtract from it the velocity of time t, which is v of x and t, and it's sitting nicely on the right-hand side. And so what this means is that v of x, comma, v of x plus delta x, comma t plus delta t minus v of x and t is then equal to dv by dx k delta xk. I'm going to put in the arguments for completeness. Xk plus dv by dt x and t delta t plus, now these terms which appear in the square bracket, we'll have a delta x squared, delta xy, delta y squared, delta yz, and so on. And that means that when you express all the delta x's and y's and z's in terms of delta t's, you will have delta t squared as a common factor for the next three terms, delta t cubed for the next few terms, and so on. So this entire bracketed section, which I have omitted, which extends to infinity in terms of the orders of differentiation, they will have delta t squared sitting outside the bracket and a whole list of garbage sitting inside the bracket. So if I now divide, and this delta xk here, I can use the fact that my delta x is related to delta t via the velocity field, and so I can now substitute for delta xk. This is vk at x and t, delta t, and so this becomes delta v, delta xk at x and t, delta times vk at x and t, delta t, plus delta v, delta t evaluated at x and t, delta t, plus terms in delta t squared, which I don't wish to write out. And now you see that I have the factor delta t common to all of the terms on the right-hand side, and this means therefore that v at x plus delta x, t plus delta t, minus v at x and t, divided by delta t, is equal to dv by dxk. Okay. I'm now going to leave the arguments out because it is perfectly clear that everything on the right-hand side is evaluated at x and t. So, because there is no ambiguity, I am free to use notation and omit the arguments as there is no lack of clarity in what I am writing. And then I have delta t multiplying this square bracket. I now take the limit as delta t goes to 0. And I get on the left-hand side, by definition, let me leave some space here because I want to write there, and this then gives me delta v by dxk, vk, plus dv dt. And then I take the limit as delta t goes to 0, the last term vanishes. Now maybe I should put the arguments into this last expression, and then I will drop them in a moment. You see, it's not a simple derivative with respect to time, because I don't have a simple function of time to describe the velocity. It's a complicated derivative, but it's exactly the same definition of the acceleration that I used for point particles when discussing their acceleration. It is the difference of velocities at adjacent times divided by the difference, time difference, in the limit as the time difference goes to 0. Implemented in an unfamiliar context, where we're describing velocity by a velocity field, and when I do that, this is the answer that I get. So v is a function of x and t, that's what the right-hand side is telling me. When I form the derivative dv dt, what do I get? You take a function of x and differentiate with respect to x, what do you get? You get a function of x, don't you? if you have a function of x and y differentiated with respect to x, what do you get? Function of x and y. If you have a function of any number of variables and you differentiate with respect to one of the variables, partial derivative, what do you get? It's a function of the same set of variables. And so what you get here is a function of x and t. Everything on the right-hand side is a function of x and t. And so we get a field of acceleration. And the acceleration field describes the fluid acceleration in exactly the same way, or an analogous way, to the way that the velocity field described the fluid velocity. If you want to know how a particle which is sitting at time t at position x, if you want to know how this particle is accelerating, then what you do is you take this field, you substitute into the arguments the values of the coordinates of the position where the particle is sitting, the time at which you want to know the acceleration, and this function will produce the acceleration of the fluid point at that position at that time. Right? It's an acceleration field. You see that everything is now written in terms of functions which are evaluated at the same arguments. I'm therefore free now to drop the arguments. Always reintroduce the arguments if ever you are in any doubt as to what a formula means. Often, the way that formulae are written by omission of arguments can be confusing. If you want to understand what the formula means, reintroduce the arguments until you become familiar with the content, and then you can drop the arguments again. Right, so this is, I'm going to switch these two factors around for reasons which will become obvious in a moment. This is my formula. I've already used that one. Just switch to one of these. And you will notice that what I have in the first term is the operator vk d by dxk operating on the vector field v. Right? And this is v1 d by dx plus v2 d by dy plus v3 d by dz. And you'll notice that this is in your standard undergraduate vector notation, is what you would have written as v dot lambda. Right? And so we can express this formula for the acceleration as v dot lambda operating on v plus dv dt. So this is a formula for the acceleration. If you're given the velocity field and you want to know the acceleration field of the fluid, this is how you calculate it. So there are two exercises here. The first is to understand and learn how to arrive from the definition of acceleration at this form. The second exercise, because this formula we use all the time, the second exercise is to memorize the formula. Don't be upset if I tell you that there are things that you want to be memorizing. It's not fashionable in this day and age, especially amongst educators, trendy, wendy educators, to tell you that you must not memorize, you must understand. Yes, that's true. But in the end, you want to be a professional person who practices competently your profession. What would you think if you were lying on the operating table? The surgeon comes in just before they put you under anesthetic, and he looks over at you and he says, yes, I did this maybe 20 years ago. I learned all about this as an undergraduate, and then it runs off. He comes back half an hour later with a large book and is paging through the book backwards and forwards, trying to find where the information was. What would you think of such a surgeon? I confess myself to him, and that is precisely how we ought to be as well, in that we need a certain body of information as professional astrophysicists. We need the information at our fingertips. The only way that you can get it at your fingertips is by memorizing it. You need to memorize a basic fundamental body of information, right? Of course, memorizing is not sufficient, because if all you've done is memorize a story, you won't find many campfires around which to tell the story, and it is just useless information. You need to understand the information as well as memorize it, so that you can then apply it when you encounter a problem that requires recall of it. You ought to have perfect and total recall of this information. If you don't have perfect and total recall, then who the hell are you? When you see the film, you'll understand the quote. All right, any questions on this? Good. It's probably time for a break, and what we will do after the break is ask a different question, and we will arrive at a very similar formula, which will then enable us to make a new definition and introduce new notation. So, according to my watch, it is now 10 to 9. We will recommence at 9. The next topic is called the material derivative. Also called the convective derivative, or the substantive derivative. What I want to do is introduce the concept of this derivative by asking a question. So we have a fluid that surrounds us, it's called air. And let's think of a property of this fluid, maybe density, maybe temperature. At every different position in this room, the air has a different temperature. Suppose that I were to take an instrument that measures temperature, and I walk around this room. Clearly, as I get to different positions, the temperature recorded by the instrument will change. Of course, I'm assuming that I've got an ideal instrument. I don't want a mercury thermometer, because that takes 5 minutes to come to equilibrium, and I want to move a bit more rapidly than that. I want a temperature measuring device that reacts instantaneously and tells me exactly what the temperature is at that position when I am there. The question is, at what rate, if I am moving along a certain trajectory in this fluid, at what rate will I measure the temperature to change? So that's the question that I want to ask. Consider some scalar field. And for the sake of definiteness, so that you've got something in your minds to think about, let's say temperature. And imagine observer with an ideal thermometer. This is just an instrument to measure this scalar field. Moving with a long trajectory I will call the position of the observer, which gives you coordinates xi. I will call the functions that deliver this position as a function of time. I will call the functions gamma. So here is the trajectory, gamma, at time t. If you want to know the position of the observer, you substitute that value of time into the functions gamma. They deliver the coordinates x, y, z of the observer at that instant. So here is the observer at time t, that is the position that he occupies. At what rate does the observer measure the temperature change? So the rate of change of T, the temperature, will be the limit as delta T to 0 of the temperature measured at time T plus delta T minus the temperature measured at time t divided by delta t so the question is, what temperature does the person measure at time t? So at time t, the observer is at position gamma I of t, so he measures temperature given to him by, well, the temperature is in general a function of position and time. You want to know what temperature the observer is measuring. So you need to substitute the coordinates of the observer and the time at which the measurement is made. The coordinates of the observer are given to you by the functions gamma I of t, and the time at which he is measuring is time t. At time t plus delta t, the observer is at position gamma I of t plus delta t, and so the temperature that he measures is given to you by the temperature field evaluated at its position at the time that he makes the measurement. And now we go through exactly the same exercise as we had previously. Let me leave out the arguments of the index. I shouldn't write indices inside arguments, that's very bad practice. This is 2 plus delta t. And so this now becomes, I apply the Taylor series again. The first thing I need to do is apply the Taylor series to this internal argument. This is now gamma at time t plus d gamma I dt at time t delta t plus terms of second order. So here I have t evaluated at gamma of t plus d gamma I dt delta t plus and then t is delta t. I now apply the Taylor series to the function t, and what I get is t evaluated at gamma of t and t, and then I've got a small quantity which augments each of the arguments. In this case it will be delta x, delta y, delta z, which is given to me by d gamma dt, so this is, if you like, delta x, and this is t plus delta t. And so this will now become t of gamma of t comma t by dt by dx evaluated at gamma of t at time t times delta x plus, yes, that's delta x, and delta x is an abbreviation for these things here. So I've started delta x, delta y, delta z in the first instance. And then you get the terms of second order. Delta x, you recall from what I've written over here, is going to be delta x is g gamma 1 by dt, t delta t. Delta y similarly is d gamma 2 dt delta t, and etc. for delta z. And so my formula now becomes t of gamma of t t. And then I have dt dx1, d gamma 1, dt dt, and so on for the others. And so this is dt by dx k. D gamma 1, d gamma k by dt t delta t plus dt dt gamma of t t plus the second order terms. And to work out the rate of change, I need the temperature measured at time t plus delta t. Here it is, left-hand side, minus the temperature measured at time t. Well, here it is. It's on the right-hand side. And so the rate of change t measured by the moving observer is equal to the limit as delta t goes to the limit of t gamma of t plus delta t plus delta t T of gamma of T, divided by delta T. And that you can see very easily gives me dt by dxk evaluated at gamma of T and T times d gamma k by dt evaluated at T times delta T. That's gone. And I then take the limit as delta T goes to 0 as well. So that leaves me with dt time gamma T. We'll recognize that d gamma by dt is the velocity of the observer as he moves through the temperature field. I won't call it v because you might think that I'm talking about fluid velocity, so I'll call it u. And this is the velocity of the observer time t. And so I get my formula, which says that this is u k t dt by dxk gamma t t plus dt by dt gamma t t. And again, you recognize that u k d by dxk is the sum u1 d by dx plus u2 d by dy plus u3 d by dz. And so this I can abbreviate to u of t dotted with none acting on t evaluated gamma t t plus dt and dt and dt t. So that is the rate at which the moving observer measures the temperature change as he travels through this temperature field. It's an interesting formula. Interesting for a variety of reasons. The first is that you see that it depends, the rate of change that he measures depends exclusively on where he is, gamma of t, his speed at the instant that the measurement is made, or his velocity at the instant that the measurement is made, and of course the function t. It doesn't depend on his acceleration. It doesn't depend on the detailed nature of the path that he follows. It depends only on where he is and how fast he is traveling at that instant. Alright, this is a general observer who is moving in some general way through this temperature field. But now let's suppose what I'm going to do is I'm going to introduce a concept, two concepts of observers which are useful in fluid mechanics. The first is what I call the dry observer. So you stand at the edge of the seashore and you watch the movement of the water in the sea. Right? You are fixed at a fixed position in a given frame of reference. That is what I mean by a dry observer. So this is an observer at a fixed position in a given frame of reference. And then I will have what I call a wet observer. The wet observer is the scuba diver. Now actually it's the idle scuba diver, because I want the wet observer to sit in the fluid and not to do anything. He mustn't swim against the current, he mustn't try to move relative to the fluid, he just lies there like a great big fat bloated whale, and he allows the fluid to carry him wherever the fluid goes. Right? That is what I would call the wet observer. This is an observer at rest in the fluid, or relative to the fluid, as the fluid moves. So this is Sherlock Holmes and Moriarty when they plunge into the water on that waterfall, they move with the fluid. That is a wet observer. And the thing about a wet observer is that the fluid velocity and the velocity of the observer coincide. And so the rate of change of t measured by the wet observer is equal to, well, there's the formula for any velocity. What I now need to do is substitute the velocity of the fluid for the velocity of the observer, because the observer is moving with the fluid. That is what the word convection means. Vector is to carry or to transport. That's why vectors are called vectors. And if you go to Italy and you fly to Italia, they will give you a brochure that says the official vector, vettore ufficiale, right? That means it's the appointed transport company for Italian air flights. And that's what the word vector means. It means to transport. So convector means to transport with the fluid. Anything that is convected is transported with the fluid. And so you can call the wet observer the convected observer, and his velocity is now the velocity of the fluid. What velocity does the fluid have where the observer is? Well, it is V evaluated at gamma t and t. And that's what I substitute for the observer velocity. And then it is nabla acting on gamma of t. T plus dt by dt gamma t and t. So you see that it's the same formula as we have for the fluid acceleration. The formula is gone, but it's the same formula as we have for fluid acceleration. Let me write it up here. The acceleration of the fluid was the fluid velocity dotted with nabla acting on v plus dv dt. Well, there it is. Except that this time it's v dot nabla acting on t plus dt dt. And so I can write that as in a similar shorthand to that one. Before I do that, I need to introduce a special symbol for this kind of rate of change. It is a rate of change. It's calculated by a particular formula, and it it should be dignified by a special name and a special symbol. So that's what we do. Denote the operator. d by dt plus d dot nam by... Now there are different notations that are used in different books. I will try to use just one notation, but let me warn you that different books have different conventions. So some books call this capital D by capital DT. Other books call it capital D, small d by capital DT. Still other books call it small d by dt, and there are a number of other notations also. But please be warned that all of these symbols mean one and the same thing. It means the rate of change as measured by an observer who is moving with the fluid, and it is called the material or the convective derivative. I like the name convective derivative because it tells you immediately that this is the rate of change measured when you are moving with the fluid. And so, the rate of change of temperature measured when you move with the fluid, this is the convective rate of change of temperature, is then dt, is partial dt by time plus d dot nav of t. And the same is true of any other scalar field, like density or pressure, that you want to introduce into the discussion. The formula for the acceleration is similarly written as dv by dt. And it is the same operator, the same concept of physical acceleration. Now, we calculated the acceleration by imagining that we were not wet observers, but dry observers. So why do we get the correct formula for the acceleration? The answer is very simple. It is that acceleration in classical mechanics is the same in all frames of reference. It is not so in relativity, but it is so in classical mechanics. And so the wet observer and the dry observer will measure exactly the same acceleration for the fluid. This is not so for anything else. All right, do you have any questions on this? Important concept. Again, you need to understand it. That means that you need to know how to deduce the formula, and you need to memorize the formula together with its physical interpretation. Any questions?
What happens if you're moving in the fluid?
If you're moving in the fluid, then you must revert to this more general formula, and you need to put in the velocity of the observer in this position, and you need to put in the trajectory of the observer into the arguments.
Does that also take into account if the fluid is moving?
You're not interested, if you're simply moving through the temperature field and you're going in a different direction to the fluid, you're not actually interested in what the fluid is doing. It doesn't enter into the equation at all. What you're interested in is how you are moving through the temperature field and what measurements you are making. The reason for introducing this in the context of the wet observer is because if you think about what we're going to have to do in order to understand the properties of fluids, we are going to have, all of the physics that you've learned is about the properties of materials when that material is at rest, right? So if you want to know, if you want to apply the first law of thermodynamics or the second law of thermodynamics to the fluid material, you have to put yourself into a frame of reference in which that material is at rest. And then you can apply the laws that you've learned in elementary physics. To do that, you need to be a wet observer. You need to be at rest relative to the fluid. That's why we introduced this concept. Any other questions? All right, then let's move on to the next topic. The next topic is a new topic, and these are called strain rates. Strain rates. Why do we want to know rates of strain? You've done elementary elasticity, and you have considered the straining of bodies which are elastic. Right? You pulled the elastic bands, you stretched cables, you maybe deformed a solid object by shearing it. The fact of the matter is that to introduce any deformation into any material, whether it's solid or fluid, you need to have an input of energy. And you must take into consideration the fact that the condition of the material, the fluid is a material. It takes energy to deform a fluid. The fluid deforms as it moves, and therefore we need to know something about how to quantify the deformation rates of a fluid. A fluid is different from a solid because a solid will deform and come to a new equilibrium position. And so you only need to consider the strain of that solid. In the case of a fluid, if you apply forces to a fluid, it will begin to flow. It yields under the applied forces. And it will continue to flow. In other words, it will undergo continuous deformation. So you can't talk about the deformation of the fluid. You've got to talk about the rate at which the fluid is deforming. And that is what we are now about to quantify. So, what does deformation entail? Well, you say that a deformation takes place if the distance between the individual points inside the object, whether solid or fluid, the distance between the points is changing. If the distance changes, you say you have a deformation. You would not consider a simple rotation to be a deformation. There has been a movement, but the distance between any two positions inside this object, they have not changed. And therefore no deformation has taken place. In order to get a deformation, you must change the distances between selected particles, right? And it takes energy to perform these deformations. So that's what we need to quantify. Consider, first of all, the way that the fluid moves. So this is the relative motion of fluid. What I'm going to ask is a very simple question. You may find the way that we have to answer it a little bit confusing until you get to understanding the actual content of the mathematics. But it's not really all that difficult. The question is very simple. I have two fluid points at time t. Let me color them with different colors. So consider two fluid points. At time t, suppose they occupy positions x and x plus delta x. So here is at time t, Here is my position x. Here is my position x. That's delta x. That means that these two points can be joined by a vector. That vector will be the difference of the coordinates of the final point and the initial point, and that gives me the vector delta x. Now, if I, so this is, these are 2 points in the fluid. I've frozen the picture at time t. I now advance the picture to time t plus delta t of this film that I've made of the fluid. And each of these 2 points will have moved to new positions. So this point may have moved to a new position here, and the orange point will have moved to a new position, say like that. So the new vector that joins them is like that. I will call this new vector delta x dashed. In time t, so this is now in time t plus delta t. In time delta t, by how much does a fluid point displace? Well, you can write the answer in terms of the fluid velocity field. The fluid velocity at time t is going to be v at, well, I need to find the velocity that the particle has when it is at position x and at time t. If I multiply that by the time delta t, I get the displacement of that point. For the orange particle, what I need to do is find the velocity of the orange point at time t. Yes, I need the coordinates of the point, the time at which I'm looking at this velocity field, and I substitute those into the arguments. So the velocity of the orange point at time t will be v of x plus delta x, because that is the position of the orange point, and I'm interested in time t. And then to get the displacement in time delta t, I must multiply the velocity by the time elapsed. Is it clear what I've done there? So I'm working at 2 different positions at time t, x and x plus delta x, and I have found the velocity at position x at time t and the velocity at position x plus delta x at time t. And so the new position of the yellow fluid point will be x plus v of x and t times delta t. The position of the new position of the orange point will be x plus delta x plus v at x plus delta x, and at time t times delta t. That is this position here. And so I can now calculate the vector delta x dashed. So delta x dashed will be, well, how do I calculate the components of a vector? I take the coordinates of the final point, I subtract from it the coordinates of the initial point. And so it is that orange expression minus this yellow expression. So it is x plus delta x plus v at x plus delta x t times delta t minus x plus v at x plus delta x t delta t. When I remove the brackets, you will notice that the x. Yes, have I done something
Should
wrong?
that be an x plus delta x in the second expression or just an x?
Oh, it's an x, thank you, yes. Thanks very much. So if I remove the brackets, that term will cancel with that term, and it leaves me with delta x plus, now it is v at x plus delta x, t delta t, minus v at x and t times delta t. And what I now want to do is use the Taylor series expansion, because I'm going to consider the limit as the separation of the two fluid points that I'm considering. I'm going to take the limit as the separation goes to 0. And so this now becomes v at x plus delta x. I'm sorry, v at x and t plus, and I can now use the information that we've had from our previous two calculations. This becomes delta x dotted with lambda on v at x and t. So I've shortcutted the calculation. Make sure that you know how to get what I've written over here. And when I substitute it into the expression, I get delta x plus v of x t delta t plus delta x dotted with lambda v x and t delta t minus v at x and t delta t. That goes with that, and I'm left with delta x plus delta x dotted with lambda and v evaluated at x and t delta t. But you can see that I'm now in a position to calculate the rate at which the separation of the particles changes. So the rate of change of separation of the fluid points is, what am I measuring in fact? What I'm going to do is I'm going to take the final vector, delta x dashed, minus the initial vector, delta x, and divide by delta t in the limit as delta t goes to 0. What am I actually measuring? Well, if you put yourself into the fluid and you move with the fluid, right, then you are sitting at position x and you're observing the fluid point near you. As the fluid moves, you are stationary in the fluid point adjacent to you is drifting away and changing its direction relative to your position. And so what I am calculating is the rate of change of separation as measured by a wet observer. So rate of change of separation of fluid points as measured by a wet observer is, well, it is d by dt of delta x. That's what I'm measuring. It's delta x whose rate of change that I'm measuring. This is the limit as delta t goes to 0 of the final separation, delta x dashed, minus the initial separation, delta x, divided by delta t. And there is my formula that relates delta x dash to delta x, and you see that d by dt of delta x is going to be delta x dot lambda on the fluid velocity x and t. This is the seminal formula from which I will be deducing all of the next few results. It is an extremely important formula to understand. So again, you have two exercises ahead of you. Understand the derivation. You should be able to reproduce these derivations at the drop of a hat, incidentally. And then once you have done the derivation, memorize the answer and understand its physical content. This formula goes with that picture. What's the word formula actually mean? Did you know that the church has formulas? I believe in God the Father, the Almighty, creator of the heavens and the earth, and etc., etc., etc. This is a formula. What is a formula?
Hazard a guess it's something you have to go about.
Yes, not quite, but almost there. It is a standard statement of an accepted truth, stated in such a way as to facilitate memorization. Right? That is what a formula is. You cast the truth into a standard form so that everybody can then learn it. That is a formula. Here is a formula. It's a mathematical formula. It's a statement of a particular truth. The content, the physical content of this formula goes with this picture. This is the explanation of what this formula is telling you. So what you need to know is that you're looking at two fluid points, adjacent fluid points, and you're looking at the movement of those 2 points and watching how they separate. At what rate do they separate? And here is the answer. It is given to you by this formula, and this is what I will use to calculate several standard results. The other thing that I should tell you about mathematics and its relation to physics or astrophysics is the following. One of the most important skills that you can learn as a physicist or an astrophysicist is the ability, when you look at what is happening outside in the universe, the ability to see equations that describe the things that you're looking at. And when you are looking at a piece of mathematical derivation like this, you should be able to look at the equations and picture exactly what is being described by these equations that is happening in the universe. So the message I'm trying to get across here is that equations are born with an interpretation. And the ability to convert phenomena into mathematics and mathematics into phenomena in your mind is one of the most important skills that you can learn. So when you do mathematical derivations like this, don't treat them as if they were jigsaw puzzles without a picture. They're not like that at all. Every statement that you make in mathematics encapsulates a physical truth. And that is what you must understand. If you develop this ability to translate formulae into phenomena and phenomena into formulae, then you will have no difficulty understanding any piece of mathematical physics. And it will give you the ability to be a good scientist. All right, we'll stop there.